Hello everyone, welcome back to the Parros Cement Techno Channel. This time, we'll explain kiln flushing operations and some of the causes. Causes of kiln flushing. In the context of cement production operations, kiln flushing is an operational disruption in which the raw material, raw mix, does not completely burn into clinker, causing the material to flow through the kiln too quickly without adequate calcination. The main causes of kiln flushing include 1. Kiln feed fluctuations. 2. Fuel fluctuations. 3. Collapse of coating layers or large coating rings. 4. Improper temperature control. 5. Changes in airflow conditions. Kiln feed fluctuations. A. Fluctuations in the raw material feed flow. The material entering the preheater system and into the kiln is unstable, or suddenly fluctuates drastically beyond the set point. This is generally caused by disturbances in the weighing feeder, or by an underfilled feeding bin. B. Fluctuations in the chemical composition of the feed material. The general standard LSF, lime saturated factor, is in the range of 98 to 100%, but suddenly rises above 102%. High LSF or high CHO content requires higher heat consumption than before, causing drastic changes in kiln operating parameters. Fuel fluctuations. A. Fuel supply. Insufficient or fluctuating supply of coal or other fuels causes insufficient or unstable calcination temperatures in the preheater system and inside the kiln. B. Fuel quality fluctuations. Changes in the calorific value of coal fuel cause a decrease in the kiln's operating temperature. Large coating or ring coating collapse. Sudden collapse of the coating or ring coating inside the kiln can cause a large amount of material to enter the firing zone at once, causing an imbalance between the material and the operating temperature inside the kiln. Improper temperature control, using low heat or firing temperatures that are insufficient to effectively calcine the raw materials. This condition generally occurs during kiln feed startup, or when adjusting the fuel consumption in the kiln's main burner and calciner burner, to the amount of kiln feed material being fed. Changes in airflow conditions. An imbalance in combustion air flow can also affect the combustion process in the kiln and preheater. This condition generally occurs during kiln feed startup, specifically between the air drawn from the preheater fan, primary air consumption, and cooling air consumption from the cooler. Early indicators of flushing are generally indicated by a sudden drop in sintering zone temperature and a decrease in kiln torque. If corrective action is not taken promptly, this condition can affect the quality of the resulting clinker or lead to high free lime levels. Restoring kiln operation after flushing requires swift and precise action by an experienced central control panel operator who coordinates with field operators to visually assess the situation. The primary goal is to restore the combustion process to normal kiln operating conditions and avoid disrupting the operation of field equipment, particularly material transport equipment in the dust collector cooler. The following are general steps to restore normal operating conditions during flushing. 1. Emergency response and impact mitigation. Stop or reduce kiln feed. The first and most critical step is to immediately reduce or stop the supply of raw mix to the kiln to stop the excess material flow. This helps control the amount of material in the kiln system. Control fuel supply. Adjust the coal fuel supply to manage the temperature in the combustion zone. Too much fuel during flushing can worsen the temperature imbalance or increase CO2 levels. Control preheater fan air draw. Adjust the preheater fan air draw by controlling O2 and CO2 levels and the top preheater temperature. Control kiln speed and monitor kiln torque. Reduce kiln speed to slow the material flow rate into the kiln, and monitor kiln torque, which typically drops significantly during flushing. This monitoring helps gauge when material begins to accumulate normally in the kiln, and kiln torque will increase again when the material has begun to burn properly. Control grate speed and clinker cooling air. Reduce grate speed and control the thickness of the material above the grate, using a pressure chamber monitor. Reduce clinker cooling air usage, to minimize dust from the cooler entering the kiln, and the cooler dust collector. Process stabilization. Maintain kiln rotation. Maintain kiln rotation unless other emergency conditions require it to be stopped. Kiln rotation helps distribute material and heat evenly once material flow is under control. Optimize air distribution. Adjust primary and secondary air flow from the cooler to ensure that firing conditions return to normal and the material begins to sinter properly. Check internal conditions. Operators need to monitor the internal conditions of the kiln via kiln cameras or visual field observations, if possible, to ensure that the material inside the kiln has begun the clinker formation process. 3. Gradual return to normal operation. Gradual resumption of feed additions. Once conditions begin to stabilize and torque shows signs of normalization, the raw material supply can be slowly resumed. The upgrade should be gradual while monitoring the kiln's response. Readjust operating parameters. Carefully and gradually return all operating parameters, temperature, airflow, kiln rotation, and fuel supply, to their preset values, leading to normal operation. Close monitoring. Conduct very close monitoring of the entire system for a period of time to ensure stable kiln operation and prevent recurrence of flushing. 4. Root cause analysis. Identify the cause. Once normal operation is restored, conduct a thorough analysis to identify the exact cause of the flushing, large coating drop, fuel fluctuation, raw material quality issues, etc. Implement corrective actions. Implement necessary operational changes, or maintenance improvements, to prevent similar occurrences in the future. Effective recovery requires experienced operators, and a thorough understanding of the production process, and kiln operating dynamics. This is a display of the kiln's operational control monitor, as it moves towards optimal operation. This display shows the operational control monitor under optimal operating conditions, with all parameters normal and under control. Thank you for watching this video. Hopefully it's useful. Don't forget to subscribe, like, comment and share this video link to your friends who need it. See you in the next video.